So we have seen so far what is meant by saying that a sequence of functions or a series of functions converges either pointwise or uniformly, okay. And we have seen that uniform convergence has many desirable properties. For example, what we proved in the last class is that when each Fn is continuous, the limit, and if Fn converges to F uniformly, then F is also continuous. Okay. And we also seen that if a sequence converges uniformly, it also converges pointwise, but the converse is false. Okay. And there is one theorem which puts some additional conditions along with the pointwise convergence, and that implies uniform convergence, and that is a theorem which we shall discuss today before proceeding further. Okay. It is a fairly well known theorem. It is known as Dini's theorem. Okay. And so there are a few additional things. Till now, whenever we talked about convergence of a sequence of functions either pointwise or uniformly, we did not say anything about the set E on which the functions were defined, but now we shall require those things. Okay. We will have to assume that E is a compact set in some metric space. Okay. E is compact set in some metric space, or you can take it as a compact metric space. Okay. And Fn and F, these are functions from E to R, okay, and Fn converges to F pointwise. Okay, that is, we will say Fnx converges to Fx as n tends to infinity for every x in E. Okay. So we want to say under what additional conditions Fn converges to F uniformly. Of course, this one additional condition is already there, okay, compact set, but that is not sufficient. Okay, we will have to put a few more things. First thing is that we have to assume that Fn and F, all of them are continuous. Okay. That is Fn and F, those are continuous functions. That is Fn, each Fn is in continuous, F is also continuous, and this Fn is a monotonically increasing sequence or monotonically decreasing sequence. Okay. It has to be a monotonic sequence. If we assume that, then we can show that Fn converges to F uniformly. Let us take one of the cases. Suppose it is monotonically increasing, okay, and let us say that Fnx is less than or equal to Fn plus 1x for every x in E and n in N. Then Fn converges to F uniformly. This is the theorem. Okay, that is, what are the additional requirements? E is a compact set, Fn as well as F, they are all continuous functions, and Fn is monotonic. Okay, here we have taken monotonically increasing sequence, but a similar thing can be proved if you take a monotonically decreasing sequence. Okay. Let us now look at the proof. Okay, let us take some x in E. Okay. Now again, whenever you want to prove Fn converges to F uniformly, means by definition what we have to do is that given epsilon, we have to produce some n0 such that whenever n is bigger than or equal to n0, mod Fnx minus Fx is less than epsilon for, and that should happen for every x in E. Okay, that n0 should work for every x. That is the idea. So this such a proof has to start with let epsilon be bigger than 0. Okay, let epsilon be bigger than 0, and let us consider some x in E. Okay, consider some x in E. Then, since we know that Fnx converges to Fx, okay, so corresponding to this epsilon, there will exist some n0, okay, so that wherever n is bigger than n0, whatever happens, we say will happen. Okay, but that n0 will depend on x, because we have only assumed the pointwise convergence. So let us call it n suffix x. Okay, so we can say that there exists n suffix x. In fact, our whole point is to find n0 which does not depend. Okay, that is the whole idea of the proof. Okay, So starting initially we do not know that, so let us take there exists n suffix n in n such that n bigger than or equal to n suffix x, this implies mod fnx minus fx less than epsilon. Okay. Now let us also use the fact that this is a monotonically increasing sequence. For each x, fnx is a monotonically increasing sequence of real numbers, and we know that a monotonically increasing sequence converges to its supremum. Okay, so each fnx is less than or equal to fx. Okay, and fx is the supremum of all those fnx. Okay, so let us rewrite this. Okay, and I will use it for this number n suffix x. I will take n is equal to n suffix x. Okay, so what do we know about this n suffix x? We of course we know that fnx at x, this is always less than or equal to fx. Okay, but because fnx minus fx is less than this, what it means is that fnx lies between fx minus epsilon to fx plus epsilon. Okay, so this must be fnx also must be bigger than, okay, this is fx will obviously less than fx plus epsilon, but this will be fnx will be bigger than fx minus epsilon. Okay, fnx is bigger than fx minus epsilon. Okay, I will just look at this part of the inequality, but that is the one which is useful now. Okay, and what it means is that fx minus this f n suffix x at x, remember everything is happening at x, this n depends on x, I am taking that particular function f suffix n suffix x, evaluating that at x, evaluating f at x, and what follows from this is that the difference between this is less than epsilon. Okay, difference between this is less than epsilon. Okay, okay. Now we know that each fn as well as f is a continuous function. Okay, each f as well as f is a continuous function. So what I will do is that I will take the set of all those points in E for which this happens. Okay, that is what is my, I'll call that and that will of course depend on this x. Okay, that will of course depend on this x. So suppose I call that let us say u suffix x. Okay, what is this u suffix x? This is defined as, let us say, set of all y in E, set of all y in E such that f at y minus f suffix n suffix x at y, this should be less than epsilon. Okay, is it obvious that x belongs to this x? Okay, because that is what this is. Okay, if you did, so first obviously that x belongs to u suffix x. Is it also clear that u suffix x is open? This is a, what is the meaning of this? This is a set of all y in E such that fy minus fnxy is less than epsilon. That means it is inverse image under the continuous function f minus fnx of the interval, you can take minus infinity to epsilon, of course actually 0 to epsilon. So it is an inverse image of an open set under a continuous function. Okay, so this is an open set. Okay, so u suffix x, and that is where we are using the continuity of f and f suffix nx. Okay, so what I will say that since f and f suffix nx are continuous, ux is open, u suffix x is open and non-empty of course because x belongs to u suffix x. Okay, alright. So what did we do? Given a point x in E, we have constructed an open set containing that. Okay, open, or which is called open neighborhood of x. Okay, then what is to be done after this? Because there is a standard compactness argument after this, because we have started with E as a compact set, cover E with all such set. So that is, so E is contained in union of U suffix x, and union is taken over x in E, right? Okay. In other words, what it means is that this, suppose you take this family U suffix x, x belonging to E, this is an open cover of E, okay, this is an open cover of E, okay. Yes. Why it is an open cover? Obviously, each ux is open set, and every x in E is contained in some ux. So if you collect all such ux, E will be a subset of this union, okay. So that means is an open cover of E. You can make a slight change in this definition. Suppose E itself is, you are taking as a metric space, then you can take this. So otherwise you can take, suppose E is a subset of some metric space x, instead of taking here y belonging to E, you can take y in that x, okay, you can take y in that x. But usually for compactness argument, that doesn't matter, okay. Okay. If E is a compact set in any metric space, then it is a compact set regarded if you regard E itself as a metric space, okay. So that really doesn't matter. Okay, so what follows after this? Because E is compact, this should have a finite subcover, okay. Okay, since E is compact, okay, you can say it's have a finite subcover means what? There exists some finite number of points. Let us say x1, x2, xk. There exists x1, x2. Let us say, suppose it happens up to xk, such that E is contained in union of this U suffix x suffix k, sorry, U suffix, let us say x suffix j, j going from 1 to k, j going from 1 to k, okay. Okay. Now what you do is you look at the corresponding n's, okay. For each xj you have n suffix x suffix j, okay, and then take n0 as the maximum of all of them, okay. So let n0 maximum of n suffix x1, n suffix x2, etc., n suffix xk, okay. Okay, then okay. Okay, then let us take, suppose we take any n bigger than equal to n0. Let us say what happens, let n bigger than or equal to n0, okay. Then what we want to show is that for, if you look at fnt for any n bigger than or equal to n0, then we want to say that mod fnt minus ft is less than epsilon, okay. Okay, let n bigger than or equal to n0 and t or x or whatever you take, okay, fine, n bigger than or equal to n0 and x in E, okay. If x is in E, x is in one of this ux1, ux2, uxk, right, right, because this is E is contained in the union of ux1, ux2, uxk, etc., okay. So every point x in E is in one of these open sets, okay. Okay, so then x belongs to this u suffix x suffix j for some j, j going from 1 to k, one of those, okay. Okay, but if x belongs to u xj means what? It means that, okay, I think in order to avoid the confusion I will change this notation here. Instead of x, let me take y, okay, so that you don't confuse that with this x we start. Actually consideration of this x is over here once we constructed this u suffix x, okay, doesn't matter, okay. So let us take some y in E, then y belongs to u suffix x, But what is the meaning of saying that y belongs to u suffix xj? Look at what is the definition of u suffix x. It is set of all those y in it for which fy minus f nxy is less than. Now here you have n suffix x suffix j. Okay, so y belongs to uxj. This means fy minus f n suffix xj at y is less than epsilon. Okay, all right. Okay, let us rewrite this. Okay, this is same as saying that that is fy minus epsilon is less than f suffix n suffix x suffix j of y. Okay. Okay. Now till now we have not used this fact. Only once we have used that fn is a increasing sequence. Okay. All right. Okay. Now for each n we know that fnx is less than or equal to fn plus 1x. This is less than or equal to fn plus 2x. So whenever n is less than m, fnx is less than fmx. Okay. Now what is the relationship between this nxj and n0? This is less than or equal to n0 is maximum of these two. So I can say that this is less than or equal to fn0 of y. Right. Okay. And we are taking n bigger than or equal to n0. Okay, we are taking n bigger than or equal to n0. So fn0 of y, this is less than or equal to fn of y. Okay. All right. Okay. Can we always say that if whatever be y, fny is always less than or equal to fy? Okay. Because again it's a monotonically increasing sequence, and fy is the supremum of all of those fny's, and obviously fy will be less than fy plus epsilon. So what did we prove? Just look at this, fy minus epsilon, that is we taken n bigger than or equal to n0 and y is in E. Okay, then fy minus epsilon less than fny and then less than fy plus epsilon. Okay. Okay. So suppose you combine these three inequalities, that is this is same as saying this, fy minus fny is less than epsilon. Okay, and this is true for every y. Okay, and for the same n0, remember we did not change n0 for this. N0 does not depend on y. Once this n0 is chosen as maximum of this, that is fixed. Okay, so if you take any n bigger than or equal to n0 and any y in E, then this inequality holds, fy minus fny less than epsilon. Okay, and that is say by saying that fn converges to f uniformly. This is what we wanted to show. Okay, fn converges to f uniformly. Okay, is this clear? Okay. So let me again remind you that what are the additional things that we are required. E is a compact set. Okay, then fn and f, they are all continuous functions, and fn is a monotonically increasing sequence. Okay, and each of these things we have used in the proof. Okay, for example, compactness we have used there. Okay, fn is monotonically increasing, that we have used here. Okay, and to say that this is an open set, each of these are continuous functions, all those things are used here. Now if you have read the introduction of Siebens' book, okay, there is one remark that he has made here, that is whenever you learn a theorem, each theorem has certain number of hypotheses and some conclusions. Okay, and then there will be proof. Proof will have several steps. Okay, and suppose you understand how n plus 1 step follows from n step, suppose you understand this for each n, that does not really mean that you have understood the proof completely. Okay, right. So what is required is to understand what is the basic idea of the proof. Okay, and what is the test for this? test for this is that you ask yourself whether each hypothesis in the theorem is essential, whether it is required. Okay. Now, how does one say that? For example, saying that this hypothesis used in this proof, that is not a good enough answer. Okay, it will only mean that this proof requires that. Okay, right? There may be some other proof without which doesn't use, and still it may be possible to prove the theorem without using that hypothesis. So there is only one way to settle such questions. Okay, and what is the way? You just drop that particular hypothesis, retain all other hypotheses, and see whether the conclusion still follows. Okay, and if your answer is no for that question, there is only one way to settle this. Okay, you have to have an example. Okay, you have to have an example where all the hypotheses are satisfied except the particular one which you are testing. Okay, which you are testing, and the conclusion is false. Okay, and the conclusion is false. Okay, so in order to understand, suppose we apply that thing here. Okay, what are the additional things we are assumed that E is compact? Okay, whether that is essential, we have to see. We have to do this by taking some non-compact set. Okay, whether Fn and F continuous, that is essential. Again, we have to see by dropping that. Okay, so certain examples we have already seen. Okay, let me just remind you. Okay, so suppose I take E as 0 to 1. Okay, E as 0 to 1. Okay, this is, in fact, this is I think the starting example. Okay, we have taken Fn x as x to the power n. Okay, we have taken Fn x as x to the power n. Okay, and what was Fx? Fx was 0 for 0 less than or equal to x less than 1, and 1 for x equal to 1. Okay, all right. Okay, now look at the theorem here. Okay, what were the hypotheses? E is compact, that is okay. Okay, okay. Now each Fn is continuous, that is fine. Okay, F is not continuous. All right. Is Fn monotonically increasing? It is not, but it is monotonically decreasing. That doesn't matter. Okay, we have seen that whether it is increasing or decreasing, that doesn't matter. Okay, is the convergence uniform? We have seen that it is not. We have seen by several ways it is not uniform. So what does it mean? That Fn and F are continuous, that is F is continuous, that hypothesis you cannot drop. Okay, okay, that hypothesis you cannot drop. Okay, okay. Let us take one more example of similar type. Suppose I want to check whether compactness can be dropped. Okay, all right. Okay, so you take E as, instead of this, suppose I take E as open interval 0 to 1. Okay, then that is not compact. Okay, all right. Okay, now suppose I take Fn of x as 1 by 1 plus nx. Fn x is 1 by 1 plus nx. Okay, does this converge pointwise to what? Suppose you fix x and let n vary, let n go to infinity, what will happen? This will go to 0, right? Okay, so this goes to 0 as n tends to infinity pointwise. Okay, so if you take f as a constant function 0, that is fx is 0 for x in 0 to 1. Okay, then Fn tends to f pointwise. Fn tends to f pointwise. Okay, is it monotonic? Okay, suppose you fix x. How are Fn plus 1 and Fnx related? It's decreasing, right? It's a decreasing sequence. Okay, so everything else is satisfied except E is compact. Okay, is this convergence uniform? How do you settle that? I have told you one easiest way of settling the uniform convergence. You look at Mn as supremum of mod Fnx minus Fx in Xn. Okay, so look at, in fact that is the one which will work in most of the examples. Okay, so let Mn be equal to supremum of mod Fnx minus Fx, where X is in E. So what does this mean in our situation? Everything is positive, so Fx is 0, so mod Fnx, okay, and Fnx is okay, it is just 1 by 1 plus Nx, 1 by 1 plus Nx for E is 0, so 0 less than X less than 1, okay, supremum of 1 by 1 plus Nx. And what do we know about uniform convergence? Fn will converge to F uniformly if and only if Mn goes to 0, okay, Mn goes to 0, okay, alright, okay. Suppose you take n to be, suppose you take x equal to 1 by n, can you do that? 1 by n lies between 0 to 1 for every n, then what will happen to this? This will be 1 by 2, okay, so I can say that Mn is bigger than or equal to 1 by 2 always. Okay, I may not calculate, it is possible to calculate the exact value of Mn also, but that is not really essential, okay. So can we say that Mn is bigger than or equal to 1 by 2 for all n? Okay. So what does it say? If Mn is bigger than or equal to 1 by 2 for all n, obviously it cannot go to 0, right? Okay. That means Fn does not converge to F uniformly. Okay, Fn does not converge to F uniformly. Okay. So that means the hypothesis of compactness also cannot be dropped. Okay. So what remains now? Fn is monotonically increasing, okay, or decreasing, whatever it is. Okay. I think I will leave that for you to as an exercise. Okay. Okay. Check on your own whether this can be dropped. Okay. Check on your own whether, that means what? You have to construct an example where Fn satisfies all other hypotheses except this. Okay. And the convergence is not uniform. Okay. If this is essential. Okay. If this is not essential, then with remaining hypotheses you should be able to prove uniform convergence. Okay. Either way you have to settle it. Okay. Now let us look at one more property related to uniform convergence, and till now we discussed about the continuity. Now let us, next is differentiability and integrability. We will first look at integrability because that is little easier to discuss. Okay, and to talk of integrability, we cannot take any arbitrary set now. We have to take an interval. Okay, so let us say that AB is an interval, and suppose, okay, you consider Fn from AB to R converges uniformly to some function f from AB to R. Of course, converges uniformly on AB. Okay, converges uniformly on AB. Then what we want to say is that if each Fn is integrable, f is also integrable, and the integral of Fn converges to integral of f. Okay, this can be proved for Riemann integrals. Okay, and this can also be proved for Riemann-Stieltjes integrals without any extra work. So let us do it for Riemann-Stieltjes integrals. So let us take a monotonic increasing function. Okay, let alpha from AB to R be monotonically increasing. Okay, then if Fn belongs to, let us use this notation again, R AB alpha. Okay, that means Fn is Riemann-Stieltjes integrable with respect to this function alpha for each n, then f is also Riemann-Stieltjes integrable and limit as n tends to infinity of integral a to b f d alpha, sorry, integral a to b f n d alpha. This is same as integral a to b f d alpha. Okay. See, we have seen an example where this is false under pointwise convergence. Okay. Okay. We have seen example of a sequence fn converging to f, but integral fn does not converge to integral of f. Okay. In fact, for Riemann integrals also this is not true if the convergence is not uniform. Okay. So this is a theorem on integration and uniform convergence. Okay, this is what we are discussing: integration and uniform convergence. Okay, so there are two things to be proved here. First is we have to prove that f is Riemann-Stieltjes integrable. Okay, and then we have to also prove that. Okay, the other thing we shall see later. Okay, to prove f is Riemann-Stieltjes integrable, we have known that one of the standard technique is that given epsilon, you should produce some partition such that for that partition up f alpha minus lp f alpha is less than epsilon. Okay, that is what we shall try to do. Okay, okay, so okay, let epsilon be bigger than 0. Then we know that each fn is integrable. Okay, so for each fn such a partition exists. Okay, for each fn such a partition exists. So the idea is that we will take one of the partitions, and if n is large enough, difference between fn and f is small. So we should naturally expect that difference between upper sum of fn and upper sum of f is small. Similarly, difference between lower sum of fn and lower sum of f is also small, and that is the idea that we are going to use. And since in doing these kind of things we will have to add and subtract certain terms 2-3 times, we shall use the usual technique of the so called epsilon by 3 proofs. Okay, that is, we will let us say, suppose if we have to add if whatever quantity that we want to show as a small quantity, we express that as a sum of the 3 quantities and show each of that as less than epsilon by 3. Okay, that is the idea. Okay, so the first step is this. Okay, since here we have taken this alpha, okay, choose you can say something else. Suppose I call it eta. Choose eta bigger than 0 such that eta into alpha b minus alpha a is less than epsilon by 3. Or which is same as saying that 0 less than eta less than epsilon by 3 into alpha b minus alpha a. Okay, this is something we can always do, right? Then since fn tends to f uniformly, what we can say is that we can always find some n0 such that whenever n is bigger than or equal to n0, difference between fnx and fx is less than this eta. Okay, difference between fnx and fx is less than this eta. Okay, so since fn tends to f uniformly on AB, there exists n0 in n such that mod of fnx minus fx is less than eta, mod of fnx minus fx is less than eta. Remember that this is for every x in AB, that is where the uniform convergence comes into picture. This is for every x in AB. Okay? This is for every x in AB. Okay. Now consider one such n. Okay, you can even take n equal to n0 or n0 plus 1 or anything. Okay, so consider n bigger than or equal to, consider some n bigger than or equal to n0. Now this Fn is integrable, okay, this Fn is integrable. So there will exist some partition P such that difference between upper and lower sum for that partition is less than whatever we want, okay, is less than, let us say, epsilon by 3, okay. So there exists a partition P in script P such that U P Fn alpha minus L P Fn alpha is less than epsilon by 3, okay. But of course this is not what we are interested. What we want to show is the difference between UPF alpha and LPF alpha, that is small, okay. And as I told you, the idea is that we shall use this, that mod Fnx minus Fx is less than eta for each. Idea is the following, okay. We want to show this, that we want to show that this is small, UPF alpha minus LPF alpha, okay. We want to show this is small. So what we will do is that we will add these terms UPFn alpha minus LPFn alpha, that is we shall write this as UPF alpha minus UPFn alpha, okay, that is adding and subtracting UPFn alpha, then plus UPFn alpha minus LPFn alpha, and finally plus LPFn alpha minus LPF alpha, okay. And we will show that each of this is less than epsilon by 3, okay, each of this is less than epsilon by 3, out of which we already know about the middle term, okay. Right here we know that the UPFn alpha minus LPFn alpha is less than epsilon by 3. Only thing remains to be shown that these two are also less than epsilon by 3, and that is where we shall use this, okay. Now to do that, let us look at this partition P. So suppose P is let us say as usual A is equal to x naught less than x1 less than xn is equal to B, okay. And what is UPF alpha? For UP, to consider UPFn alpha or UPF alpha, you have to look at the corresponding supremums in the subinterval xi minus 1 to xi. So suppose let us say that mi is equal to supremum of let us say fnx for x in xi minus 1 to xi, okay, and let us say mi star is equal to supremum of fx for x in xi minus 1 to xi, okay. All right. Now again look at this. What this says is mod fnx minus fx is less than eta for every x in AB, okay. So let us rewrite it, okay. What this means is that fnx lies between fx minus eta to fx plus eta, that is I will just rewrite this inequality, okay. Okay, what does this mean? That fx minus eta is less than fnx is less than fx plus eta. This is true for, remember that is important, this is true for every x in AB, because that is what follows from uniform convergence, okay, for every x in AB, okay. Hence for every x in this xi minus 1 to xi also, okay, right, that means each fnx here will be less than fx plus eta for every, okay. So can I say from here that mi must be less than mi star plus eta, okay, mi. So I will say that, so what I will get is mi is less than, because remember here you are taking supremum of fx and here you are taking supremum of fnx, and fnx is less than fx plus eta. So we can say that mi is less than mi star plus eta. Okay, this is for every I. Okay, for every I. Okay, then so if we look at UPF alpha, or let me write UPFN alpha, that is nothing but sigma I going from 1 to n. Okay, if it is Fn, it is mi, mi into delta xi, no, not delta xi, but delta alpha I, mi into delta alpha I, and UPF alpha, that is nothing but sigma I going from 1 to n, mi star into delta alpha I. Okay. So if each of this mi is less than mi star plus eta, okay, I can say that this is less than sigma I going from 1 to n, mi star plus eta into delta alpha I. Okay, right? Okay. But what is this? Suppose I split this, it is sigma mi delta alpha I, that is nothing but UPF alpha. Okay, that is nothing but UPF alpha. Okay, and plus eta times sigma delta alpha I going from 1 to n. Okay, right? And this is something we have calculated several times. Sigma delta alpha I is nothing but alpha b minus alpha a. Okay, alpha b minus alpha a, and so this is, and we have chosen eta in such a way that eta times alpha b minus alpha a is less than epsilon by 3. Okay, so what is the what is the that result? That if you look at the difference between UPF alpha and UPFN alpha, that is, in other words, what I want to say is this: UPF alpha minus UPFN alpha, this difference is less than eta into alpha b minus alpha a. Okay. Okay, it is the other way. Okay. Less than eta into alpha b minus alpha a. Okay. And this is less than epsilon by 3. This is less than epsilon by 3. Okay. Alright. Now, in a similar way, if you look, is this clear? Okay. In a similar way, if you look at the lower sums, okay, instead of taking supremum, you are taking infimum. Okay. Instead of taking lower sum, so a similar relationship will be true there. Okay. Similar relationship will also be true there, and we can in a similar way show that the difference between the lower sum of Fn and lower sum of F, that will also be less than epsilon by 3. Okay. Okay. And so suppose you combine all these, you will get finally that difference between UPF alpha minus LPF alpha is less than epsilon. Okay. That will show that each if each Fn is integrable, F is also Riemann-Stieltjes integrable. Okay. Right. Again recall, see what is the idea here? We are writing this UPF alpha minus LPF alpha as the difference, as the sum of these three quantities. Okay. And UP, if for large n, UPFN alpha minus LPFN alpha, that can be made less than epsilon by 3, because Fn is integrable, and when n is large, the difference between mod Fnx minus Fx can be made arbitrarily small, and that is why the difference between the corresponding lower sums and the corresponding upper sums can be made arbitrarily small. That is the idea. Okay, that is the idea. Okay, okay. Fine. So now what remains? We have to show this. Okay, that limit, we already know that this integral exists. Now we have to show that limit of integral a to b f and d alpha, limit of that is same as this. Okay. Now to do that, okay, let us recall something that we have proved earlier. Okay, okay, I think I will remove these things. Okay, do you remember we have proved this, that if you look at any integral a to b f d alpha, we have proved that if f is integrable, mod f is also integrable, okay, and absolute value of this is less than or equal to integral a to b mod f d alpha, right. This is what we have proved, okay, alright. Then what I will say is that again consider, let us say this n0 eta, everything is as we have already chosen here, keep this same things and again choose some n bigger than or equal to n0, okay. Okay, so consider n bigger than or equal to n0, consider n bigger than or equal to n0 and look at the difference between these two integrals, okay. Integral a to b f d alpha minus integral a to b f n d alpha, okay. I can write this as follows, integral of this as integral of a to b f minus f n d alpha okay, right, that is from the properties of the integrals, okay. Now I use this, okay, okay. So what it means is that this is less than or equal to integral a to b mod f minus f n d alpha, okay, right, okay. Now again look at what we have said here, okay. For every x in, if n is bigger than or equal to n0, for every x in AB, mod fnx minus fx is less than eta, okay, mod fnx minus fx is less than eta. So what follows from that? This function, if you look at this function mod f minus fnx, its value is less than eta for every x in AB. So what can we say about the integral? It will be integral will be less than eta into alpha b minus alpha a, okay. So this will be less than eta into alpha b minus alpha a, okay, right, and we have already seen that this must be less than epsilon by 3, less than epsilon by 3, okay, of course, and epsilon by 3 is always less than epsilon, okay, okay. So what did we show? That given any epsilon bigger than 0, okay, there exists n0 such that whenever n is bigger than or equal to n0, the difference between these two numbers is less than epsilon, okay, right. That is same as showing that this, that is same as showing this, okay. So again recall what we have shown is that if fn converges to f uniformly and if each fn is integrable, then f is also integrable and integral of fn converges to integral of f, okay, alright. Okay. Now let us write an implication of this for this series, okay, right, because that is something that is more useful in practice and that is what you require very often, okay. And what is that? Okay, okay. Suppose sigma fn, n going from 1 to infinity, is uniformly convergent, okay. Let us say this is converges uniformly, okay. Since we have used f already, we will use something else. Since converges uniformly, let us say to some function g, okay. Then what does this mean? That if you take the sequence of partial sums Sn, okay, then Sn converges to G uniformly, okay. Now let us assume that let us assume the same hypothesis here. That is, suppose each Fn is integrable, okay, then it will mean that G is integrable, and then integral of Sn will converge to integral of G, okay. But what is integral of Sn? Oh, let us say what is Sn? Sn is f1 plus f2 plus fn. So integral of Sn, integral a to b Sn d alpha, that will be same as integral of a to b f1 d alpha etc plus integral a to b f and d alpha, okay, integral a to b f and d. So in other words, what I can say is that if sigma fn converges to G uniformly, then G is okay. If G also belongs to R a b alpha, that means G is also integrable, and integral a to b G d alpha is same as sigma n going from 1 to infinity integral a to b f d alpha, okay. That is, integral of the sum is same as sum of the integrals. Of course, this is something we already know about the finite sums. The question is about the infinite sums. In case of infinite sums, it is in general false, okay. It holds only when the convergence is uniform, that is important, okay. It holds when if the series converges uniformly, then the series formed by taking the integrals converges to the integral of the sum, okay. In other words, this is roughly expressed by saying that you can integrate this series term by term, okay. That is, you can interchange the operations of integration and summation. Suppose you write this in the full form, what is the meaning of this? This G is nothing but integral summation of, that is, suppose I write in the full form, this will be integral a to b sigma fn d alpha. This is same as this sigma, okay, this is here sigma n going from 1 to infinity, sigma n going from 1 to infinity, integral a to b, this should be fn d alpha. In other words, what this means is that the operations of integration and the summation can be interchanged, okay, okay, and this can be done provided the convergence is uniform, okay. That is what this theorem says, okay. So we will stop with this. In the next class we shall discuss the differentiation and uniform convergence, okay, relationship between differentiation and uniform convergence.